Hi there, this is a rather unusual and heavy piece of test equipment that just arrived on my bench. It's a CLARE flash tester A203B with insulation measurement capability. It is extremely heavy, about 20 kilos, and someone has put a transparent plastic shield over the front, either for electrical safety or to prevent unauthorized changes of settings, quite possibly for both reasons. The left meter goes to 5 kilovolts and the right one has two scales, an upper in megohm at 1 kilovolt and a lower in milliamps. I found this on eBay and it cost me all of £5.50, that is less than $7. Shipping was nearly 3 times of that on account of being so heavy. Needless to say, the unit is long obsolete. The only user manual I found was for the more modern but also obsolete A203ES. I did not find any service manuals or schematics of any of these units. Just from a quick glance, the A203ES user manual seems to be of limited value for my unit. The two look and seem to be quite different. The A203ES has various current delivery settings controlled by a key switch, and there is no mentioning of a timer in the manual. The controls in my unit seem to be for the meter, not the actual current delivery, but judging from the timer on light, there appears to be a timer. Well, to be honest, I bought this less with an eye of making it work, more for useful parts, but of course, getting it running would be nice. Maybe I can figure it out without a manual. A closer look at the controls. There is a supply switch and an on light. That is the on-off switch and pretty clear. You can also see the timer on light. A big round knob is labeled HT volts, standing for high tension. That will be setting the up to 5 kilovolts output, which will be probably shown on this meter, showing the high voltage in kilovolts AC. A closer look at the other meter. The top scale is megohms and not linear. It goes from 0.4 on the right to 10 on the left, followed by inf, standing for infinity. The lower scale goes left to right and shows the current from 0 to 2.5 milliamps. The reason the upper scale says megohm per kilovolt is that the megohms are obviously depending on the set voltage. At 1 kilovolt, a resistor of 1 megohm passes a current of 1 milliamp, which explains how the scale was drawn. At 5 kilovolts, the same 1 milliamp means a resistance of 5 megohm, so one has to multiply the megohm with the kilovolt number. A reading of 10 at 5 kilovolts means 50 megohm. The controls on the right are a light test complete, a control to set IR trip megohm. I suspect that IR stands for insulation resistance. I guess that if the value is set to 50, any measured insulation resistance lower than that will cause a trip, in other words, a fail. The round knob at the most right is set inf. I guess this knob is to set the instrument to show inf if there is nothing connected to the output as kind of a calibration. No idea what the black round thing is. It has a perforated cover. There's a red light and a white push button. They are labeled flash fault reset. I think this is to reset if the instrument trips as mentioned earlier. The rear is very bare. There are 2 high voltage connectors, but sadly no probes or cables came with the unit. On the very right is the power cord, which is very short, less than half a meter. Next to the gland for the power cord is a strange round connector with 3 sockets that look very vintage. A closer look at the type label and a sticker that the last safety test was in May 2015. Let's see what we got inside. There are 4 big screws on the back panel, so let's start with those. It seems the whole upper part of the housing will come off, but not yet. I think I need to remove some screws on the front first. Removing the transparent cover and then the standoffs for the transparent cover. Yes, now the top shell of the housing feels loose and I can lift it off. There's a lot going on here. The output voltage is controlled by a variac on the primary side of the high voltage transformer. And there appears to be a timer. Here's a 10K high voltage resistor that generated so much heat that it discolored the PCB over the years. Obviously the unit was heavily used before. The two op amps are good old 741s. The sticker looks like from the manufacturer and shows a tested date of May 1990. I turned the unit to give you a better view of the stuff behind the front plate. A small transformer is hanging between the 2 meters. Actually, there are 2 more small transformers under the toasted PCB. The other PCB has a lot fewer components. Its tested date is June 1990. So we may assume this unit may have been made sometimes towards the end of 1990. Since this PCB sits on top of the high voltage transformer, it has the thick red high voltage wires connected and a neat row of 9 2.2 megohm resistors in series. I think at least some of its job is to drive the voltage readout meter. The high voltage itself comes from this massive transformer, which is probably responsible for half of the unit's weight. All in all, it looks to be in good condition, and if nothing else, it has a decent parts value. Even better if I can get it to work, which will need some improvisation as the unit did not come with any cables and clearly expect some high voltage probes to be connected on the rear. I stuffed some cable in there which does make contact, as I verified with the multimeter. To be clear, this is not a good or safe permanent arrangement, but all I want to find out if the unit even works. I connected my Arvo 8 to the output because it has a 2.5 kilovolt AC range, but I also turned the variac all the way anti-clockwise, which is hopefully the lowest position. Once I turn on the power to the mains outlet to which I connected the unit, an unexpected loud piercing sound gave me quite a shock and I quickly turned it off again. Okay, so the main switch of the unit was actually in the on position. Let's try that again. Yes, same thing happens, but now I control it with the unit's power switch. Again, and this time I remembered the fault reset button. It did not work immediately, but finally the fault light is off and the buzzer quiet. Now I know what that round black thing next to the fault light is. It's a buzzer, and a very loud one at that. So the unit is now on and I try the voltage knob. Apologies for blocking the meter, but there was absolutely no movement. The needle stayed at 0 and the Evo meter confirmed there was 0 output voltage. I'm missing something here, but since I have no manual, the only way is to study the unit itself. Let's start with a timer, which can be easily unplugged from its socket. It's an Omron H3C3 set to 10 seconds. Thankfully, Omron has printed the pin out on the unit. From what we see, 2 pins, 2 and 7, are needed to activate it. And there are 2 sets of contacts that are driven by the timer, but not the same way. Clearly the upper set is driven differently from the lower set. Turning the unit reveals the mystery. Pins 5, 6 and 8 are for contact driven by the selected time, but pins 1, 3 and 4 are for contact that is instantaneously driven as soon as the timer is running. Datasheets for the timer are available on the web from Omron, and this thing is way more complex than what you would expect. As a start, it can do timing from 500 milliseconds to 300 hours. That alone indicates this is an electronic device, and indeed the block diagram confirms this. My unit is set to sec, meaning seconds, as the time unit, which can be changed using this screwdriver operated selector, and mode A, which is another setting that can be changed with a control below the A. The other 4 modes supported are complex and really not important here. Mode A basically means that the instantaneous contact is activated immediately and the other contact after the elapsed time t, and then stays activated until the power to the timer is removed. The point of all this is that the timer needs to be activated, and since there isn't a button on the front that does this, I suspect it's the strange 3-pin connector on the back. Armed with that knowledge, I suspect that pin 7 is connected to mains neutral because of the black wire used, and that is indeed the case. Making sure the unit power switch is in the on position so the live from the plug is connected, I tested live from the plug against pin 2 and there is nothing. I expected this because obviously the timer wasn't running in my earlier test. So the key question is, does timer pin 2 have a connection to the plug on the rear? Indeed it has. This is the same test from the other side. The leftmost socket of the plug is connected to pin 2 of the timer. What about the right socket? I suspect that this is connected to mains live through the unit's power switch, and indeed it is. And the third socket above the other two? It turns out to be connected to earth. So now it is clear, to activate the time I need to bridge the two lower sockets in this connector, like so. Again, that is of course just for testing. Let's see what happens. No change. The unit behaved exactly as before. And this time I suspected an interlock with a fault indicator, because it makes no sense to let the timer run when there's a fault. But in hindsight, it turns out this unit isn't that sophisticated. The failure of this test was simply due to my wire bridge making a bad contact. But at least the fail led me to improve the arrangement and add a real switch, which is definitely how the unit should be operated. Adding a switch was easy because I had a very suitable mains rated button with two wires handy from my video number 138 on the Solartron AS1414.2 power supply. Now this button is a latching type, which was a bit inconvenient for the Solartron, where momentary action is all that's needed, but here I think the latching is needed to keep the timer running. Let's see how this works. Turning the unit on and clearing the fault. When I press the button gingerly so it does not latch, the timer on light comes on momentarily but then goes off again. This confirms the button needs to be a latching type or a simple switch. But turning it on and then leaving it, well, "10 seconds are a long time if you're waiting." Yes, the test complete light comes on. And the unit stays so until I turn the timer off. Now the crucial part, do I get any output voltage? I set the voltage very low. Yes, as soon as the time is running, we get nearly 1 kilovolt and also some current on the meter on the right. Success, the unit is working. It is a bit annoying that one has to start the timer to set the output voltage. But anyway, the AVO shows there is a high voltage coming from the output. The camera angle is slightly to the side, but the output is indeed a little below 2000 volts, so the AVO and the built-in meter are in agreement. I connected my BM869S in parallel with the AVO using a divide by 1000 probe. The 1.0243 volts it shows is therefore 1024.3 volts, which agrees with the meter on the CLARE. I run a test at 1 kilovolts and let me freeze the video for a moment. The AVO 8 has a rather low input resistance of about 2.5 megohm in the 2500 volt AC range. This means, according to what's written on the meter, megohms at 1 kilovolt, I would expect the needle very close to the left of the two, but instead it is showing over 5 megohm. Increasing the voltage to close to the maximum the AVO can handle, and you can see how the megohm needle moves towards the 2. Let me freeze again. 2.46 kilovolts, and with 2.5 megohm load we should see nearly 1 milliamp, but instead it's approaching only 0.5 milliamps. I think the current/megohm meter has been wrongly calibrated, and I think this was done on purpose, because there is a sticker on the box. If the meter was calibrated to show megohm at 2.9 kilovolts instead of 1 kilovolt, my results would make sense. Unfortunately, I can't test at 2.9 kilovolts because the AVO 8 is already at its maximum. I have no idea why the previous owner had chosen this value, but I would rather have the original. There are 4 trim pots in this device, 2 on the PCB above the HV transformer and 2 on this one. Each PCB contains a trim pot labeled METCAL, meter calibration. I suspect this is the one for the current/resistance meter, but first I want to record the way this pot is currently set. In case it's the wrong one, I can restore the setting. The best way is to measure its resistance, of course, with the power off. It is very tricky to get to the legs of the pot directly, so I have a look where the traces go to find a more convenient spot to probe. This is a simple single layer PCB, so a torch shining from underneath reveals it all. The Metcal pot is wired as a simple variable resistor, not a divider, and I found two convenient places to measure its currently set resistance, 2.1148 kilo ohm, and I'm sure I have the right trim pot for the current meter because it responds to my probing. Remember, the power is off, so this deflection comes from my multimeter measuring the Metcal trim pot resistance. But first I need a more precisely known resistance instead of the impedance of the avometer. Therefore I put a 1 megohm resistor on the output. With 1 kilovolt I should see exactly 1 milliamp or 1 megohm on the scale. I can't do this too long though, because 1000 volts and 1 milliamp means the resistor is loaded with 1 watt. I'm not sure if this resistor is rated for 1 watt or 2 watts, but let's assume the worst. Running the test clearly shows the miscalibration. Instead of 1 megohm, the meter shows over 2 megohms. For adjusting trim pots in a device running 1000 volts at the moment, I'm extra careful and touch the screwdriver only at the isolated handle and use only one hand, not touching anything else. Because of the timer, I have only 10 seconds to do it, so several attempts were needed to get it right, but you get the idea. One test point isn't great, so I decided to use a 10 megohm resistor at 5 kilovolts. That should read 0.5 milliamps or 2 megohm. The 10 megohm resistor reading only 2 megohm is because the megohm scale is only valid at 1 kilovolt, so at 5 kilovolts I should read 5 times less or 2 megohm. This test loads the resistor with 2.5 watts, but this is a 3 watt type, so it should be okay. Okay, I need to up the voltage, but here we are, 5 kilovolts. The current approaches the 0.5 mark, but remains slightly below. When the timer finishes, it's clear that the null/inf point isn't set quite right, which explains it. Apparently, if you want precise measurements, you have to check and set this with the inf pot on the front plate every time when changing the output voltage. Back to the 1 meg test resistor and 1 kilovolt voltage. It measures fine, as you can see, but what I want to know is if the trip still works. For this, I run the test repeatedly, and before every test I nudge the trip setting a little closer to the 1 mark. Finally it trips. The dot on the trip dial is very close to the 1. The few markings in this dial shows this is a very non-linear setting, so it can't be more than a ballpark value. For exact trip values, one would need to use the method I just showed, using a known resistor to produce the desired current and adjust the trip dial until the unit just trips. Then there is the problem that the high voltage is not stabilized and therefore fluctuates a little bit with mains. The unit doesn't trip, but repeating the same test a few seconds later without changing the dial, and suddenly it trips. Maybe the mains voltage has just increased a little, or maybe it's because the resistor has changed its value as it heats up from repeated tests. I decided to put a 1 microfarad 50 volt cap on the output and treat it to 1000 volts. As a precaution, it's in a bag containing fragments in case of rapid disassembly. The results are disappointing because nothing spectacular happens. It causes an immediate trip even at the least sensitive trip setting. The needle of the Arvo 8 and the bag barely moves. I ran this test repeatedly. This is how it looks on the unit itself. I tested the capacitor afterwards and it still measured okay, but I decided to rather put that capacitor into the bin. I guess the trip feature of the CLARE tester prevents major damage and the max current is only 2.5 milliamps. The later models of the 203 testers apparently can go up to 125 milliamps and have a flash trip bypass burnout button to, as the manual says, observe arcing in the item under test. My unit doesn't allow that. Maybe it could be modified, but I will leave that for another day. I decided to keep the unit for now and play with it some more, but make it a bit more safe. Gone are the temporary high voltage wires held with sticky tape. Now I have proper DIY high voltage probes that work absolutely great. How did I make these? Very simple. I got a pair of test leads with shrouded straight banana plugs on either end and simply grind one end down until it fitted into the high voltage sockets on the rear. I also exposed the ends. They do not look very pretty, kind of chewed up, which they really are, but I don't care about this. And yes, the wire is not rated for 5 kilovolts, but as long as you carefully route your cables and never touch them when the unit is on, they should be okay. A reasonably safe solution for the timer connection was more work. I searched all kinds of obscure plugs, but I could not find a match. So I fabricated something using bent paper clips and a terminal block. I also used some junk box parts to make a better switch assembly. The previous solution from the Solartron PSU video was awkward because the only isolation from the switch contact was a bit of heat shrink, which is why I only held it on the cable. But 2 layers of heat shrink is fine for the plug part, which isn't going to be touched all the time once it's plugged in. You may also spot that the mains lead is now black. The half-meter lead that came with the unit was very cumbersome to use, so I replaced it with a 2-meter long piece I had lying around and marked the terminal block in the unit at the same time. After all these improvements, I ran 2 further tests. The first is a Chinese mains transformer. Since it has 2 separate bobbins for primary and secondary, I did not doubt that it would pass the 5 kilovolt test, but it's nice to have confirmation. The second test was a piece of Vero board. I wanted to see if there would be any arc over. I ran the test at 2.5 kilovolts and indeed there was. Interesting, the first couple of flashovers did not trip the 203B. Maybe they were too short, but the last one finally did. And that's it for now. In case you wonder, those giant crocodile clips came from the Kaiwitz test set CAT05 I reviewed in video 143. If I find something interesting to test with the CLARE A203B, I will make a follow-on video. Please contact me if you have an interesting piece of equipment that you want to send in for review, repair, or if you want to donate it to the channel. If you enjoy my videos, don't forget to like and subscribe. There are many more projects, repairs and reviews coming up, and it would be great if you decided supporting this channel by becoming a Patreon. Thanks for watching.